Okay, so when you close your eyes and picture a kangaroo, what do you see? I mean, be honest.
I think for, 99% of people, it's a cartoon, right?
Totally.
It's a mother with a cute little Joey peeking out of a pouch, maybe. Maybe wearing boxing gloves, bouncing around.
Yeah, the Australian outback. It's iconic for sure, but it's also seen as, well, quirky.
Quirky is exactly the word, a biological oddity.
Right. A bit funny looking, a bit strange. But we have a source text today that it completely shatters that image. It's a research doc called The Kangaroo and Leaping Towards Survival.
And the picture it paints is, it's not of a cute, bouncy animal, it's of a sophisticated, high-performance machine.
It really is.
The source makes this really compelling case that the kangaroo isn't just an animal that happens to jump. It argues that the kangaroo is and I'm quoting here, a biological operating system.
Biological operating system. I love that phrase.
It's great, isn't it?
It implies this total sync between software and hardware, like a fighter jet or something.
Exactly. And that's really our mission for this deep dive. We're going to try to dismantle the engineering of the jump.
So we're not just, reciting biology facts.
No. We're going to explore how this animal manages to basically break the rules of energy consumption, how its bones act like smart materials, and why engineers have tried for decades and failed to build a robot that can do what it does.
And we have to talk about the hypothesis in here that honestly sounds like something out of a sci-fi novel.
The seismic communication.
Yeah, the idea that they're basically using earthquakes to send text messages.
That part is fascinating. But to get to the how, we really have to start with the why. And the source kicks off with this foundational idea called the default mode hypothesis.
This was the first thing that really grabbed me.
Yeah.
Because, normally we think about movement as a choice. I'm standing still, now I choose to walk.
Right. For us, for dogs, for horses, the default state is stability. We're built to stand. Jumping is. It's a deviation. It's an interruption.
It costs us something extra.
A lot extra. We have to mentally and physically prep for it. But the source suggests the script is totally flipped for the kangaroo.
Completely flipped.
The default mode hypothesis says that for a kangaroo, jumping isn't a choice. It's the baseline. It's the factory setting of their entire nervous system.
So wait, if I'm getting this right, for them, standing still is actually the effort.
In a way, yeah. The source uses this great analogy. Think of a normal car at a red light. You put it in neutral.
Right, the engine's idling, but it's relaxed.
Exactly. The kangaroo is like a drag racer idling in drive with a foot slammed on the brake.
Okay.
The engine is revving, the tension is there, it wants to go. Staying still requires active work to not go.
That's such a powerful image. But is that just a nice metaphor, or is there, actual physiological evidence in the text for that?
Oh yeah, there's hard evidence. The source points to the spinal cord. If you look at the motor control centers, even when the animal is totally motionless.
Just like grazing or something.
Yeah, just staring into space, the nerves aren't quiet, you see these rhythmic, repetitive firing patterns.
So the electrical signal for jump is just playing on a loop.
Essentially. The system is humming with the rhythm of the jump before a single muscle even twitches.
Wow.
And it extends to the muscles themselves. The text highlights the gastrocnemius, that's the big calf muscle, and the thigh muscles.
In us, when we sit down, those go soft.
Right, total mush. But in the kangaroo, those muscles stay in a state of elastic tension. They are preloaded, the energy is just sitting there.
So they're perpetually buffering the next launch.
That's the idea, and it's why walking is so awkward for them. You ever see a kangaroo walk slowly, using its tail like a crutch?
Yeah, looks clumsy.
It's because they're fighting their own springs. Jumping is the release. The source actually proposes this really interesting study to prove it. They want to compare the brain activity of a resting kangaroo to a resting horse.
And what would they be looking for?
Well, the hypothesis is the horse's brain would show a rest and digest signal, calm. But the kangaroo's brain will look almost the same as its active state, a state of permanent launch readiness.
It just reframes the whole animal. It's not lazy, it's a coiled spring.
Exactly.
But let's move from the software, the nerves, to the hardware. Because you can be ready to launch, but if you're launching a 200-pound animal 10 feet in the air, that landing is violent.
Extremely violent. The G-forces are huge.
Yeah, I know I'd shatter my ankles. So how do they handle that impact over and over? The source really focuses on the tail, calling it the fifth limb.
Yes. And this is where we have to unlearn what we think we know. We see the tail as a kickstand or a counterweight.
A standard textbook definition. Balance,
It does do that, sure, but the source argues we're massively underestimating it. They describe the tail as a mechanical energy battery.
A battery, so it stores power.
Kinetic energy, yeah. Think about the hop. When it lands, gravity is trying to crush it. That impact creates a huge amount of force.
Which, in most animals, just gets wasted as heat or shock.
Correct. But the kangaroo's tail is packed with these incredibly dense elastic tendons. As the animal lands, the tail bends, it stretches those tendons.
So it's absorbing the shock.
It absorbs it, holds it for a split second, and then whips it back out to help propel the animal into the next jump. It's recycling the impact.
So it's like regenerative braking in an electric car.
That's a perfect analogy. It captures the energy that would otherwise break their bones and turns it into fuel for the next move.
That explains why they look so fluid when they really get going. They're not powering every single jump from scratch.
No, they're riding the wave of the previous one. And the source raises a fascinating question about this. It asks if the internal structure of the tail changes based on where the kangaroo lives.
You mean like a desert kangaroo versus a forest one?
Exactly. A red kangaroo in the open desert needs raw speed and efficiency. It probably needs a tail with more elastic fibers, a better battery.
But a gray kangaroo in a forest needs to be more agile to dodge trees.
So it might need more muscular control in its tail, not just pure bounce. The tail is a specialized tool, tuned to its environment.
But speaking of durability, we have to talk about the bones. You mentioned the bone paradox. Even with the tail helping, those leg bones are taking a hammer blow every single time.
This is one of the most incredible parts of the source. The text hypothesizes that kangaroo bones act as nonlinear springs.
Okay, nonlinear spring. Break that down for me.
So a normal spring, a linear one, is predictable. You push it with 10 pounds, it compresses an inch. 20 pounds, 2 inches.
Right, a straight line on a graph.
A nonlinear spring changes its behavior based on how hard you hit it. The source suggests that on a light hop, a soft landing, the bone offers a certain kind of elastic absorption. It's bouncy.
But on a hard landing, like if it's escaping a predator.
On a violent high-speed landing, the internal structure of the bone actually shifts its response. It becomes stiffer. It changes how it distributes force. It stops being bouncy and starts being a progressive shock dampener.
So the bone itself is smart.
In a materials science sense, yes. It's an intelligent material that alters its properties to match the threat level.
That's wild. We spend millions developing smart materials for cars and skyscrapers, and it's just hopping around the outback.
It's all one integrated system, but there's still one piece that really confuses scientists, and that's the fuel economy.
The energy paradox.
Yeah.
This was the part where I started to question basic physics.
It really does defy the standard laws of locomotion.
I think everyone gets the basic rule. I run faster, I get tired faster, my car burns more gas at 100 miles an hour than at 50, speed costs energy.
That is the universal rule, except, it seems, for the kangaroo.
How is that even possible?
Well, the source points out that as a kangaroo speeds up, its oxygen consumption, its metabolic rate,
Right.
It doesn't rise proportionally. The graph actually flattens out.
So they can go faster without burning much more fuel.
Exactly. Now, for a long time, the thinking was just that it was the rubber band theory, right? The tendons.
The elastic recoil we talked about.
Right, and that's definitely part of it. But this source introduces a much more radical idea: neural energy recycling.
Okay, this is the part I had to read twice. This involves the brain.
It does, and this is where it gets really weird. The hypothesis is that as the kangaroo goes faster, its brain actually does less work.
Wait, less? That seems completely backwards. Faster movement should require faster reflexes, more processing?
I know, it's counterintuitive, but think about it in terms of expensive versus cheap control. When you're learning to drive a car, you're thinking about everything.
Right, check the mirror, foot on the brake. It's exhausting.
It burns a ton of glucose, it's metabolically expensive, but once you master it, you just do it. You hand it over to automatic circuits in your spine.
Autopilot.
The source suggests the kangaroo takes this to an extreme. At slow speeds, they have to use that precise, expensive neural control. But once they hit a certain velocity, a kind of flow state, the brain effectively withdraws.
It just logs off.
It pretty much disconnects from the micromanagement. It hands total control over to the reflexive circuits in the spinal cord and the legs. So the body is working harder, but the command center, the brain, is idling.
That is brilliant. The faster they go, the less they have to think.
And the brain is a huge energy hog. So shutting it down saves a massive amount of fuel. It contributes to that flat energy curve.
Wow, they literally stop thinking to move faster.
And the source proposes a study for this, too, measuring glucose use in the brain at different speeds. The prediction is you'd see brain fuel usage drop just as physical speed ramps up.
It just shows how integrated this all is. But this isn't just for showing off. This all ties back to survival in their environment.
The Australian environment, one of the harshest places on Earth. Heat, drought, huge differences.
And the source argues jumping is actually a tool for thermal regulation.
It is. Think about it. A dog runs horizontally. A kangaroo moves vertically and horizontally. That pumping motion forces air around the body like a bellows. It's a built-in cooling system.
So the movement itself cools the engine.
Right. And their stops are interesting, too. We assume they stop because they're tired. The text suggests these are calculated thermal discharges.
It's like a pit stop just to dump heat.
Exactly. A rhythmic cooling cycle, all managed by that same operating system.
Okay, but there's another interaction with the environment here that is just, it's mind-blowing. We've talked about heat, gravity, now we have to talk about the ground itself.
Seismic communication. This is the wildest hypothesis in the whole text.
When I read this, I thought, okay, now we're reaching, rabbits thump their feet to warn of danger. That's common.
Sure, but this is way more complex than just watch out.
Right.
Think about the physics. You have a huge animal, maybe 90 kilos, slamming into the earth with rhythmic force that sends seismic waves through the ground.
And in the outback, the ground is often hard and dry, so it can carry those vibrations really well.
Incredibly well. And the source hypothesizes these aren't just random thuds. The intensity, the timing, the frequency, it creates a unique signature.
A Morse code of gravity.
Kinda, yeah. A kangaroo miles away could feel that thump through its feet. And the data in that thump could be really detailed.
Like what kind of data?
Well, the signature would reveal mass. So, I am large. The cadence reveals condition. A fast, consistent rhythm says, I am healthy. And the location is triangulated through the ground.
That is just, it's like a biological internet running through the dirt, a non-visual social network.
It solves a huge problem in a vast landscape. You can stay connected to your mob without ever seeing them.
You have to wonder what that's like to feel the ground buzzing with chatter. Hey, Frank is over by the creek.
It's amazing. And this brings up a frustration the source touches on. If we understand this biological operating system so well, why can't we build a robot that does it?
We've tried, right? Boston Dynamics and others.
They've all tried.
Yeah.
And they usually fall over. Or their batteries die in 10 minutes. They're incredibly inefficient.
Why do they fail? We have carbon fiber, we have the computers.
The source argues it's because of a fundamental misunderstanding. Roboticists tend to be modular thinkers. They build a leg, attach to a body, then write code to make it move.
They build it in parts.
Right. But the kangaroo is an indivisible system. You can't separate the tail from the torso or the nerves from the rhythm. The robot fails because it doesn't have the integration.
We're copying the shape, but not the philosophy.
Exactly. It's a lesson in holistic engineering. And that leads to the source's conclusion, which zooms out to look at the future of evolution.
Because the world is changing, it's getting hotter, resources are more spread out.
Right. And usually we see animals as fragile in the face of climate change. But the source argues the kangaroo model low energy use, high heat tolerance, physical intelligence is actually futuristic.
It's not primitive. It's an advanced response to a harsh world.
As the world gets harder, the kangaroo is already designed for it. The source calls it engineering against gravity, but it's also engineering against scarcity.
It really changes how you see them. They're not just surviving, they are optimizing.
The final takeaway for me was this. The kangaroo doesn't jump because it can. It jumps because it must.
It's survival encoded into motion.
And it forces us to ask a tough question about ourselves. We solve problems by adding more energy, more complexity. The kangaroo solves them by using physics and letting the body do the thinking.
Which leaves us with the thought I want to leave everyone with today. If the kangaroo represents the solution where the body is a battery and the brain does less work to go faster, what other primitive adaptations out there are actually more advanced than our own biology?
It's a humbling thought. Maybe the ultimate intelligence isn't a bigger processor, but knowing when to shut it off.
Absolutely. So the next time you see a kangaroo, don't just see a bouncy marsupial. see a masterclass in physics.
And maybe, just maybe, see if you can feel them texting you.
I'll be checking for vibrations from now on. Thanks for joining us on this deep dive into the kangaroo code.
Thanks for having me.
We'll see you in the next one.